Okay, thank you, Wojtek. So since my talk will be about information theory in an industrial research lab, let me first introduce the group in the industrial research lab where I am in. And so we have a small information theory group of about 7 people, 4 of whom are permanent employees of HP, 3 are visitors. So I have a core of 4 people in the information theory group, which moves between 4 and 7 according to the time of the year. And so we have been doing information theory for many, many years, 15, 20 years at HP. And when Alon invited me to give this talk, he said, well, why don't you show how information theory is applied in the industry, and in particular data compression? Since you know data compression is not so popular these days, you can show the impact of data compression. And when I started thinking of the talk, I said, well, in order to apply information theory, you don't really have to be an information theorist. So why don't I first talk about why it may have some impact to be an information theorist and apply information theory in the industry. And that's what this talk is going to be about. So we all like the fact that information theory, it's a formal discipline, right? It's a mathematical discipline. Well, in a very general way, I can define it as a formal framework for areas of science and engineering for which the notion of information is relevant. And we like the fact that it's a formal discipline, but that has very, very specific applications: data compression, error correcting codes, cryptography, without which technology as we know it today wouldn't exist. Now, there is the mathematical theory. We work on measures of information. We work on data representation, on codes. And we work with some tools, which are data models, fundamental bounds, decoding and coding algorithms, efficiency of algorithms. And actually, most of us, that's the part that we like. Right? And yeah, we are very proud that also has a lot of applications, but we like the fact that it's a formal discipline. And then we can ask, well, for the industry, as I said, there are lots of applications. It's a fundamental area of science, but the fact that it's formal or the fact that it's very mathematical is not of relevance. What matters are the applications. So the first question, the first legitimate question that one could ask is, when you look at the mission of our group, you know, in the industry, groups have missions. So many years ago, we phrased what would be the mission of our group. And we wrote something like this: research the mathematical foundations and practical applications on information theory, generating intellectual property and technology for the company through the advancement of scientific knowledge in these areas. And so for the company, apply the theory and work on the applications makes lots of sense. But in order to do that, you don't have, as I said, you don't have to be an information theorist. To do data compression, most people, I mean, may come to some of you as a surprise, but most people who do data compression are not information theorists. And they don't have to be information theorists. This applies a little bit less to error correcting codes, but it's also true. So a legitimate question is, why invest on advancing the theory? And then you can have some simple answers to that, like long-term investment, prestige, visibility, give back to society, all of which you can answer by saying, well, why don't you give money to universities? So, yeah, most of you also would like that answer. But what I'm going to discuss in this talk is a different type of answer, which is, well, yeah, we know that these are enabling technologies. Now, how about differentiating technologies? Something that differentiates you from your competition. So everyone can do, say, data compression. Can you do it a little bit better? And in order to do it a little bit better, I will try to show, I don't know if I'm going to succeed, that it's worth being an information theorist rather than just applying information theory. So this is the goal of this talk. And in order to achieve this goal, I'm going to consider a few case studies. The first one will be on data compression. And it will show you how to go from what universal source coding is about, so from doing universal context modeling to image compression standards. I will talk about JPEG-LS, a little bit about JPEG 2000 for many reasons, one of them being that, well, as usual, lossless data compression is much closer to information theory, to the basis of information theory, than lossy data compression. The other one is that I have been more involved in JPEG-LS than in JPEG 2000. The other example is one which so far, in terms of all this spectrum from theory to practice, has been a little bit less successful, which is the DUD algorithm. So how we went from a formal setting for universal denoising to actual image denoising algorithms. And I'm stopping there. I'm not going all the way to say application to the industry, etc., because yet we haven't been successful in that respect. It doesn't mean that we are not going to be. It's probably too early, but I'm not completing there the full circle. And the last application is one for where codes, and in this case constraint coding, are used in a completely original way, or the way they were not originally thought of. And it shows you, first of all, the importance of serendipity. So why doing basic research in some areas may have impact in areas that you didn't expect. And also the importance of interdisciplinary research, and why being in a research lab, an industrial research lab, has many advantages. So let me start with the data compression, and I will spend a few slides with some basis of universal data compression. Again, this goes in the spirit of what Alon said, that data compression these days is not very popular. So let's take the advantage. There is a full room, or almost a full room here, to hear about some of the traditional stuff in data compression. So traditional Shannon theory assumes that you have a probabilistic model of the data, and that with that, with respect to that model, you aim at compressing the data optimally. Okay, we all know that. And we all know also that when we talk about a code, a lossless data compression code, we are equivalently talking about a probabilistic model. Why? Because of Kraft inequality. If you have a code, this means that there is an implied probability distribution that you are assigning on the sequences. And conversely, if you have a probability distribution, so you have a model for your data, you can build a code that assigns approximately. Is this working? It was working.
One of the two is working.
Okay, doesn't. Try to make this work. So if you have a code, you can. So if you have a probability model, you can build a code which assigns approximately minus log of the probability of the string to the data. For example, a Shannon code.
You want the load that is started?
Oh. So, given a model on sequences of length n, a model, we'll call it P. So arithmetic coding provides with an effective mean to sequentially assign a code word of length close to minus log of P to this sequence via some ideal code length assignments, which are given by the probability that you assign to the current symbol, given all the past symbols. So the importance here of arithmetic coding is that, first of all, the model can vary arbitrarily and adapt to the data. So the model can be anything that can adapt, that doesn't have to be fixed. And the importance of importance of arithmetic coding is that now the coding system can be separated into completely, or in principle, completely separate parts, which is the model and the coding unit, and the problem for the coding unit has been solved. It's an arithmetic code, although, I mean, there is some research, there have been, until recently, quite a lot of research on how to do it more efficiently in terms of complexity, but basically, the problem of data compression is a problem of probability assignment. So we care about the model, okay? And universal data compression is the part of information theory that deals with the optimal description of data in the absence of a given model. So first, a connection to practice, that in general, in practice, the model is not given to you. Nobody's going to tell you the probability distribution of the data you want to compress. So the first question that comes to mind is, how do we make the concept of optimality meaningful for individual data sequences? So what does it mean for the universal data compression for the code to be optimal? And the answer is with respect to model classes. So we want a universal code to perform as well as the best model in a given class. So we have a class of models for any string where the best competing model changes from string to string. So you compare your code to a class of models, and for each string, you compare yourself to the best model in that class. And you want this difference, this redundancy, you want to make it as small as possible. So the first observation here is that universal coding tells us how to encode optimally with respect to a class. It doesn't tell you how to choose the class. So here you have a second problem related to applications to practice. How do you choose the class of models you are going to compete with? So some possible criteria are complexity. If there are no efficient coding algorithms for that model class, you'd better not compete with it, because you're not going to create any useful data compression. The other answer, which is the one to which I will devote the next couple of slides, is that you determine your model class based on prior knowledge that you may have on the data, things that you may know about the data. And why is that important? Well, let's get here to our first fundamental bound. A criterion for measuring the optimality of a universal model with respect to a parametric model class is something that most of you heard about, which is resonance lower bound. Now, some of you may be thinking, especially those who did work on universal coding, how come until the last slide you were trying to convince us that we are going to work only with individual data sequences, and now we are putting a probability distribution on your data when you apply resonance lower bound. So, okay, allow me to do that. I could give this talk without even mentioning any probability distribution other than as a modeling tool, but not assuming that your data is coming from any probability distribution. It's just simpler to do it this way. So resonance lower bound tells you that for every model piece, so for every code, you, on average, if you have a parametric model class with some nice properties, then on average, your code will assign at least as many bits as the entropy plus some penalty due to universality that has to do with the size of your model class. In this case, since it's a parametric model class, with the number of parameters in the class. Okay? This D here. So the larger the class, and that makes sense. What the bound does is to quantify that penalty. The larger the class you are competing with, so the larger is your penalty. Okay? So, and there is an intuitive way of doing it, which is looking at it, which is the first method you could think of. The first method of data compression, universal data compression method you could think of, is to check all your parameters, okay, and then encode what is the best parameter for your specific data sequence, and then encode the data with respect to that parameter. The more parameters you have, this part increases, whereas your fit to the data is better, so this part decreases, and there is a trade-off. And what this bound is doing is quantifying this trade-off. Okay? So the conclusion from this slide is that the number of parameters affects the achievable convergence rate of a universal code to the entropy. Okay? And there is a sentence I will use throughout the data compression part of this presentation, is that don't learn what you already know, because it has a cost. Okay? So before we get to image compression, that's the last slide, one very successful and popular model class is that of tree models, and which are basically a more efficient parameterization of Markov process. Was introduced by Rissanen in '83. Then there are other words like formalizing the definition of tree models. And basically the idea is to have a variable memory Markov source. Okay? So you look at the past. So you have a data sequence, you have the next input bit, and you look at what is the context in which it appears. You can consider it like in a tree, and you say, well, the last bit was a 0, then a 1, a 0, a 0, and if that's your model, if that's your tree model, that's where you stop, that's your context. But these are all possible contexts for the next bit, and the challenge is either to find the best tree to represent your data, and again, you have this trade-off. You want more parameters or less parameters. Or maybe you don't have to find the best tree. Maybe you can average over all the trees and encode that way. So the nice thing about these models is there are two nice things. One is that it actually represents actual data. So in many instances, that it's not practical to represent the data with a Markov model because you have too many parameters. Actually, tree models work much better. And the second one is that there are efficient algorithms. Either to find the best tree, here you have two examples, or the popular CTW algorithm, which you probably all know, which actually says, no, don't find the best tree, you have to average over all possible trees, and you can do it in a very efficient way. So let me now move to lossless image compression. And let me give you some background. I was working in those areas when I was when I joined IBM. I was working with Rissanen. And at the time, if you remember, in early 90s, IBM wasn't doing very well. And there was this push, we have to start to be more practical in the labs. You have to do things which are practical. So my manager came and said, well, why don't you try to apply these things? I had never thought of image compression, and I liked bounds and algorithms. And so you have to be more practical. You have to try to apply this. So I started working on lossless image compression. Now, some applications of lossless image compression, because you know, the most popular thing is lossy image compression, right? So why would you do lossless? Well, there are many applications in which you do lossless. You have a long list here. You have, of course, medical imaging, satellite imaging, images, any image that was meant for further analysis and processing. There are many applications. And there is right now an international standard which hasn't changed since 1998, which is JPEG-LS, in which we were involved. Now, the first thing I noticed in image compression, and this brings us to this universality versus prior knowledge, is that when you apply these universal algorithms for tree models, it doesn't work. It's a disaster. And there are two reasons. One is some typical structures of images are not captured by the model. So we were not choosing the right model class. And second is that we were not choosing the right model class for another reason, is that we were learning things about images that we already know. And I will list these things right now, but say, if you apply any of these context-based algorithms or Lempel-Ziv to an image, the compression is very small. And the reason is that eventually it learns the patterns, but eventually maybe in a long time. So the modeling approach that we took was to limit model classes by the use of prior knowledge. So what is this prior knowledge? So for example, images tend to be a combination of smooth regions and edges. So in general, in an image, in a natural image at least, you have a small region and you have edges. And in the small region, I mean, for ages, people have been using predictive coding. So why discard it? So predictive coding was used for years, and it encodes the difference between a pixel and the predicted value of the pixel. And another observation that people have done is that this prediction error tends to follow a Laplacian distribution. So although the center of the distribution, that's an observation we made late, depends on the context, at least the shape tends to be Laplacian. And so what makes sense is to use an autoregressive model plus Laplacian, where both the center and the decay are context dependent. So we are mixing here this prior knowledge with context models. The context gives you the dependency of the bias of the distribution and of the variance of the distribution. Okay? So we will use a prediction, as traditionally done, a fixed predictor, but we will also have an adaptive component to that predictor, which is context adaptive. So let me talk a little bit about context for image. So first of all, in these models, contexts are formed out of a finite subset of the past sequence. We are not going to look into the whole past. First of all, because it creates also an ordering question, a very interesting ordering question. How do you scan the image in order to get the most meaningful past? And not only, it's not just how you scan the image, it's how you quantize the knowledge you have of previous pixels. Maybe it's more the most significant bit of the pixel which is 2 behind is more important than the second most significant bit of the pixel which is right after the image. So how do you order all that information? So we are not going to deal with that. So we take a causal template of the current pixel to encode the image. And the other important model is that the conditional probability model for prediction errors is what we call a two-sided geometric distribution. So it's a distribution which is like a discrete Laplacian with some bias which we can assume is between 0 and 1. And the reason we can assume that is that we have an adaptive bias cancellation. So we cannot make the distribution be centered completely in 0, because it could be that it's shifted, but we can at least make sure that this bias is not more than 1, because otherwise we would shift more the predictor. So the question we ask ourselves is about complexity constraints. And the reason is, are sophisticated models worth the price in complexity? So we know all these algorithms for context sources are linear time. But in practice, they are quite expensive. And the other thing is that even arithmetic coding, at the time at least, was not an easy sell in many applications. If you tell an engineer in building a data compressor, he wouldn't be happy to do an arithmetic code. I don't know, I have been a little out of this area the last few years. I don't know how current this assertion is. If it's, although maybe with newer technology, arithmetic coding is an easy sell, but it definitely wasn't an easy sell 10 years ago. So the question is high complexity required to approach the best possible compression? So here I'm going back to the thing, to the premise I had at the beginning of the talk about enabling technology versus differentiating technology. And where it may be important to be an information theorist rather than applying information theory. And the idea that we tried to apply in JPEG-LS was to apply judicious modeling, but not to improve compression, but to reduce the complexity. Can we achieve the same compression that you were getting with very complicated arithmetic codes and with very complicated models with very simple ideas by really understanding what is behind these models? And I think we succeeded. And one of the things that you have to take into account here is that this separation principle between modeling and coding that we discussed before, that made the teaching information data compression so easy, so you have the model and then you have the encoder, is not so clean when you cannot use complex models or when you cannot use arithmetic coding. So if you are not going to use arithmetic coding, so your models should be easily encoded for with some other models, with some other means. Okay? So luckily, these two-sided geometric distributions, for example, can be easily encoded with some very surprising, in some cases, variants of Golomb codes. And here is the work where we show that, although I'm not going to lie you here, and you can see from the dates, the use of these codes in JPEG-LS precedes the investigation of all possible codes for the different cases of two-sided geometric distributions. However, at the time we had an intuition of what should be these optimal codes. So let me give you here, just in one slide, what is this LOCO-I algorithm. So JPEG-LS is based on the LOCO-I algorithm, which is from low complexity lossless compression of images. And it was published first in a conference in '96, then in journal in 2000. And the basic components are a fixed plus an adaptive prediction, which is context dependent. It has conditioning context based on quantized gradients. So you don't take as a context the value of the surrounding pixel, but rather the gradients in the surrounding area. You have a two-parameter conditional probability model, which is the two-sided geometric distribution, which we learn adaptively. And then there are low-complexity adaptive coding matched to the model. So that's where what I said about the model not being completely detached from the coder. So these are variants of Golomb codes. And then we have rank length coding in flat areas to address the drawback of symbol by symbol coding. Because if you don't use arithmetic coding, you will be doing symbol by symbol coding, which means that you will spend at least 1 bit per symbol, which in flat areas is too much. So in those areas, we detect them and we do rank length coding. So this algorithm has been very successful. It's at least well, first of all, I have checked, there are many websites right now of companies selling hardware and software for JPEG-LS. I have not followed that, all that. I know that in HP it's in the printers pipelines, it's in scanners. I know it's in the medical imaging standard in DICOM. And actually it has also been used by NASA, and it was in the Mars exploration rover. And actually I have a few pictures for you. So these are pictures of the landing. So it's, most of the pictures you've seen from Mars are actually lossy compression. There are a few that they think are very valuable, and they did it lossless. And some of them, those are navigation pictures. So in the landing of the rover, so that's where the pictures they took. And these are some Mars landscape compressed with JPEG-LS. But that's the thing about lossless compression. You cannot do any nice demo, because that picture could also be uncompressed and you wouldn't know. So let's move now to spend a few minutes in JPEG 2000. So as you know, there was and there still is a very successful standard JPEG that is still being used, that was from the late 80s, early 90s, which was based on DCT. And when the standardization committee started working on JPEG 2000, the idea was to support resolution and SNR scalability. That was partially supported in the previous standard. So we want a single bit stream to be parsed efficiently to represent the image at different qualities and resolutions. Okay? So how do you achieve resolution scalability? That's through wavelets. And I'm not going to talk about wavelets, but because I prefer to talk about things that I more or less know about. So, and again, that's the part of compression that is mostly dealt with people, signal processing people, than people from information theory. What I'm going to talk a little bit, because we had some involvement there, it's about SNR scalability. So what was done in terms of SNR scalability at the time, which basically bit plane coding, which is an implicit quantization. So you send bit plane by bit plane, and you can cut whenever you want, so that to have different qualities of your data according to your resources. But this brings an interesting question, and that's where, again, we are back to probabilistic modeling. So where is it used? So first of all, it's used in the traditional way. When you do bit plane coding, you do the coding, which is context-based. And again, we are back to the same questions that we asked before, okay, for binary data in this case. But also, there is a question of ordering. So I said, you're sending a bit plane, but in what order do you send your data? Okay? In traditional cases, what you would send is bit plane by bit plane. And each bit plane, say, raster scan within a band. Okay, I'm talking now about in each frequency band. Okay, I'm not talking about the different frequencies. So what we came up with back in '98 was with a principle that tells you, well, you shouldn't be sending your bit planes in any order. You should describe information in order of decreasing expected distortion per expected bit of description. You should first send the most important information. Now, if you have an expected distortion and expected description, first of all, what you need is probability on your data. So you need to model your data on the same, much in the same way that you have to do it in lossless image compression. So we were able to show that under very general conditions, this expected distortion per expected redundancy is greater for significance decision than for refinement decisions. So what does these things mean? A significance decision is when a wavelet coefficient, you still don't know if it's non-zero. So far what you have seen are zeros. Whereas a refinement decision is for a coefficient that you know is non-zero, and you're sending, more bits. Okay? And for significance decisions, we were able to show that D over R increases with the likelihood of the coefficient becoming significant. So again, it's important to model those. You have to estimate the probability of a coefficient becoming significant, and then if it has more probability, you send it first. However, this messes up the whole thing, because the way you model probabilities is, the way we did it is with a causal template. But if you don't know, if you have sent this bit, then you have a problem, okay? Because you don't know what you can include in your causal template. So we have further simplified through empirical observations. One is that coefficients with non-significant neighbors are likelier to become significant. So this way we came up with what we call sub-bit planes, which are used actually in the embedding in JPEG 2000, which is to to separate the bit planes into what we call sub-bit planes, which are ordered according to the expected distortion versus expected rate in decreasing order. I'm not going to go through the details of how we do that, but let me show you what is the effect. The black curve is what is the D versus R that you would get with bit plane coding. At the end of each bit plane, we do the same because we send bit plane by bit plane. But in the middle, what we get now is a much more convex curve, which dominates the one that you would get with bit plane coding. And the nice thing is that this goes together with other features of JPEG 2000, where you encode block by block, and then you do rate distortion optimization. And so the fact that we have a convex curve enables this rate distortion optimization. And I'm going to stop here talking about compression, because otherwise I will run out of time for the other topics. So let me now talk a little bit about denoising. So the denoising problem is actually a natural extension of the work on prediction and compression that we had been doing before that. And so the reason is that what is denoising? You have a discrete source of data, the sequence that we will call X. We assume that the data is corrupted by noise, which will be modeled as a discrete memoryless channel, and you get your corrupted data Z, and your goal is to denoise that data to come up with estimates of the original data in order to optimize some fidelity criterion, which could be to minimize the number of symbol errors, square distance, etc. And I don't need to mention all the applications. We are going to talk specifically about image denoising, but you can think of denoising other types of data. Okay? So what is the DUDE algorithm that we came up with? The DUDE algorithm is a denoising scheme that is universal in the same sense that you think of universality in data compression. So it's universal in that no prior knowledge or assumptions are made on the data generating mechanism. You don't even assume that there is a data generating mechanism. It is asymptotically optimal in the sense that it approaches the performance of the best scheme that has full knowledge of the statistics of the data. In the same, again, the same sense that you define optimality in data compression. And it's practical in the sense that we can do it with very low complexity. So the theoretical impact is that universal denoising is possible and can be accomplished in linear time. The practical impact so far is over 20 patents filed or granted, most of them already granted, mostly in image compression, although also in compression of other types of data. But as I said in my introduction, we haven't still really applied that, as far as I know, to any product. So the contributors to this work, well, Tzachi Weissman at the time was also in our group at HP Labs. Now he's at Stanford. It's the group from HP Labs. And Sergio, at the time, also was visiting MSRI, which is close to HP Labs in the Bay Area. So how is the DUDE algorithm done? So basically, we do it in two passes. In the first pass, we gather statistics of symbol occurrences per context pattern. So first of all, let's assume for the moment that I have fixed what is the context. Okay, what type of context we are looking at? Say 4x4 blocks surrounding the pixel. You tell me which one, and I'll fix the context. Okay, I'm not telling anything yet as to how to optimize this context. Okay, and so we look at the context samples and we gather statistics on symbol occurrences per context pattern, and from there we estimate the noiseless. So we are looking at noisy data, so we gather statistics about noisy data, but based on those statistics we estimate the noiseless symbol distribution given the context pattern and the noisy sample. So we look at the posterior distribution. So we estimate from the data the probability of Zi given its context, and based on that, we estimate the probability of Xi given the context and given Zi. And in the second pass, we denoise each symbol. We use what would be the optimal denoiser based on the estimated posterior.
The context pattern is fixed. It's not variable like in the tree.
No, it's fixed. It's fixed. It's fixed. In this explanation, how it varies, I'll discuss it a little bit later. Okay? And we denoise each symbol based on this estimated posterior. So the intuition behind the decision formula, which I'm not giving here, is who do you believe? Do you believe what you see? So Zi, the context, or Zi, or do you believe the context? Okay? And do you believe the global statistics, what they tell you, or do you believe what you see? And that's how that explains the formula we came up with. And now going back to the context template, the size, as we know, must be carefully chosen for the same reasons that we discussed in data compression, but there is here a basic problem that makes it essentially different from data compression. So in principle, and in a very rough way, how do you do it in data compression? You encode your data. If you don't have any complexity constraints, you encode your data with all possible context. You check which one is the best. Then you send your context model, and you send your encoding with respect to that model. Now, in denoising, you cannot do that because you don't have access to the clean data. So you don't know which context is the best. Okay? So one way in the paper, in our work, what we did is to show that if the context grows in some way with respect to the length of your data, you are okay. Okay? However, it's not a very satisfying reason, and we are still investigating that problem. We have a recent work on how you choose the context size given your data in an adaptive way, not in a way that depends only on the length. So we have applied due to image compression, and what I can tell so far is that in what we call salt and pepper noise, and salt and pepper noise is this kind of noise where with some probability you throw salt white to your pixel, and with some probability you throw pepper black to your pixels, and with some probability there is no noise. Okay? So with an error rate of 30%, that's how Lena looks with salt and pepper noise, and that's how it looks after applying the dude to it. So it's not the dude as described. I'll discuss later what variants you have to make to the dude in order to get this type of results. But what I can say is that we are over 3 dBs better than the previous state of the art, and for those who work on image processing, 3 dBs is a lot. It makes a lot of difference. So definitely, dude is the state of the art in image denoising for this type of noise. Now, what are the main challenges in doing image denoising? Well, it's again the same thing as in data compression, a modeling problem. Why? Because, as I said, the main component of dude is that we want to model the conditional distribution of a pixel given its context. But we have limited data. We want to model that distribution, but we don't have too much data. And if we take large context, then they appear a few times, so we cannot model the data. And we want to infer from that distribution the probability of xi given zi and given the context. So if we have, first of all, in image compression, you usually have a large alphabet, so you have many parameters. So there is a large number of parameters, therefore there is a high learning cost. So what we did is we leveraged the same semi-universal approach from image compression. rely on prior models, on prior knowledge, and don't learn what you already know, which is the premise that I used in image compression. The only difference with the data, and these are important differences with image compression, is that here the context data is noisy. So your context is itself noisy data. Okay? And the other one is that the models are non-causal. The causality constraint that we had in data compression, we don't have it here. Okay? So what are the main tools that we have used? Contexts are based on quantized activity levels. So when we talk about the context of ZI, it's not really we don't make counts like in the Dude paper. We don't take counts of pixel values. We take counts of pixel values conditioned on quantized activity levels. And this determines the shape of the distribution. We could parameterize. We don't do it in the best results we have. We don't do that. But we could parameterize these distributions, like we do also in image compression. And for each sample, this shape is centered at a predicted value. Again, we use the fact that smoothness, you don't have to learn it. It's there, and you know it's there. And again, so the holy grail is to incorporate a safe amount of prior knowledge to reduce the richness of the class. So as I said, do this state-of-the-art in salt and pepper noise. It's competitive for Gaussian and real-world noise. For Gaussian noise, it's not the state-of-the-art. It's close to it, but it's not. And there is still room for improvement. So let me now, as a final part of my talk, move to a completely different topic, which is constraint coding. And as I said in my introduction, this is an example of serendipity in basic research. So we work together with a very prestigious group of device scientists and physicists in HP labs who have developed, maybe you saw lots of press releases and whatnot about the memristor. So what is the memristor? So the memristor, and it's much more complicated than what I'm making it here, but just for this talk. The memristor is a bipolar device that can be switched between high and low resistance states by applying suitable voltages. So if it's in this state, in the on state, okay, so we have a very high resistance. But if you apply the opposite voltage, you switch it, and you have low resistance. Okay? And based on memristors, HP and probably other companies are trying to build memories based on crossbars of non-isolated devices. Okay, so what you have is a crossbar. So you have conductors, nanoconductors, here and here. Okay, and if each intersection you put a memristor, and you apply a voltage. And if you apply one voltage or the opposite, you switch the memristor for the on state to the off state, and conversely. And for reasons that I'm not going to discuss here, but I'm going to summarize in this sentence, the overhead circuitry is fixed per crossbar. So there is some circuitry, some CMOS circuitry that you have to add for every crossbar, and that's a fixed overhead. Therefore, in order to increase the density, you want the number of conductors, the number of devices per conductor, which we will call M, as large as possible. Okay? So that's the goal, to have M as large as possible. Now, so one day, one of these physicists came to us, actually to Ronnie Roth, who he had been working on constraint coding. Him and Eric Ordengley had been working for years on constraint coding. Starting in the 90s, HP contributed to the DVD standards and used constraint coding for that, for a completely different reason that I'm going to mention now. And he said, this physicist had a very good intuition. He said, well, if I have these crossbars, and I want to write a memristor, I have to apply this voltage. I use some energy. But there are leakage currents, okay? Because if I apply in this column V, there are all these sneak paths in which there is half the energy going. Okay, I have instead of 2V, I have V as a potential. So I'm using too much energy, and this, so the current leaks, and this limits the amount of conductors I can put, and hence it limits the density. How can I solve that? And actually, he had the intuition that, well, I would have less current if I can limit the number of devices in low resistance state. Well, and immediately we thought, well, that's a constraint code. So how do we apply here constraint codes? What we want to do is to encode the data to limit the number of low resistance. Here by low resistance, I mean that there are one devices per row and column. So this is a 2D constraint coding problem. So we want to create arrays in which binary arrays, which are m by m, in which there are at most m/2 ones in every row and every column. That's a legal array. Okay? And the proposed approach by Ordentlich and Broad and others in our group was to use, again, as I said, for an m by m crossbar, limit to m/2. And the reason we are limiting to m/2, again, I'm not going to discuss it right now. There are good reasons for that, and not to limit to some other fraction of conductors. And what I'm going to describe here is what Eric and Ronnie came up with, which is the bit flipping code, which encodes m-1 square bits into an m by m array with at most m/2 ones in every row and column. So as you can see here, the redundancy is about 2m. Okay? So they are paying 2m, and we'll see later how good this 2m is. They are paying 2m in order to get the redundancy, in order to get the constraint they wanted. So let me go through an example of an encoder. Okay, and I don't have time, I'm going to go only through the encoder and not the decoder. So here you have a 4x4 array. Okay, and the first thing, m is 5. Okay, so they can encode a 4x4 array in a 5x5 array. Okay, so the first thing they do is they add zeros to the last row and column. Okay. Next step, they go row by row and they see which row doesn't satisfy the constraint. If it doesn't satisfy the constraint, they flip it so that it will satisfy now. So for example, here we have 3 ones in the first row. We flip them, and now we have 2 ones. So it does satisfy the constraint. Well, we do it row by row, and then column by column. So this column doesn't satisfy the constraint. You flip, and now it does satisfy the constraint. However, you caused now this row not to satisfy the constraint. So you do it again, row by row. Flip this row, and now the second column has to be flipped, again until you satisfy the constraint. You have to repeat these steps, and you are guaranteed to terminate. Why? Because in each step, you reduce the number of ones at least by 1. So in the end, you won't have too many ones, so you are guaranteed to satisfy the constraints. Now, the decoder, and I'm not going to go through the example now, it's done but very simply. You have to add modulo 2 4 bits. That's it. So the decoder is trivial. And I'm not going to go through the example. So the problem here, the only complexity problem could come in the encoder. The decoder is really trivial. And it comes in the encoder because the best bound they have on the number of, worst case number of iterations is between linear and quadratic in M. Okay? So they came up with an alternative approach which is based on antipodal mappings that only requires 2 iterations, 1 row and 1 column, so it's linear time and encoding and decoding. Okay, and they presented that last ISIT, I think. The redundancy of this approach, of the bit flipping approach, as I said, is 2m bits. And probably you attended one talk earlier this week by Farzad Parvaresh on what is the best you can do. So what is the number of m by m arrays with at most m over 2 ones in every row and column? This is work by Eric, Farzad, and Ronnie. Well, they showed, and actually they have a better bound than this today. This is an older bound, but it's good enough for this talk. They showed that actually the best you can do is of this type. So the redundancy is rho m, where rho is 1.4251. So 2m wasn't that far away from the best you can do. But of course, that you can do with very, very high complexity. Okay? So with low complexity, they can achieve 2m. And actually, they also developed efficient ways to combine this code with error-correcting codes. Okay? And this, we hope, will make the difference. And going back to the beginning of my talk, I hope that this will differentiate HP from other people doing memristors. So this type of intellectual property. Okay? But that's, again, too soon to tell. Thank you.
We have time for questions.
So what about the possibility of having a variable size context in the Lemaisin format, like you did in the compression? Is it feasible?
Well, by variable, yeah, it is. But by variable, we mean, in compression, by variable, what we meant, I mean, it is variable over the data because you learn it. But in the end, you could, if you did it in 2 passes, you will learn it in the first pass and it will be fixed. By variable, you mean that the size of the memory is variable.
Yeah.
Well, no, in the DUD you can do the same. Actually, in the paper, it's what we look at is a neighborhood. We have k to each side. I mean, the same k to each side, but you could do it different. You don't know. That's not essential at all.
No, if it's context dependent, then data dependent.
The thing is, if it's data dependent.
Yeah, that's what I mean.
Yeah, and there we have some new ideas, and actually, we presented when I think Krishna was that last year or 2 years ago in ISIT. We presented a paper on, we can talk about that later, about learning the best context size.
Any other questions? Okay, thank you. This is not mine.
Hmm? Oh, yeah.